Okay, now we'll discuss the third theorem on group isomorphism. The statement is like this: suppose N is a normal subgroup of G and H is just a subgroup of G, then in that case we need to show that Hn by N is isomorphic to H by H intersection N, which means that there must exist a mapping F defined from H to Hn by N, which is from this one, H by H intersection N to Hn by N, which is 1, 1 on 2 and homomorphism. But to prove that one, we just need to show that there exists a mapping F defined from H to Hn by N, which is a homomorphism and on 2. Then after that we can apply we need not show that it is 1, 1, but after that we can apply the first isomorphism theorem. So now let us just recall this important theorem. If N is a normal subgroup of G and H is just a subgroup of G, then in that case N will be a normal subgroup of Hn. So that's why the quotient group Hn by N can be formed. Now similarly, H intersection N will be a normal subgroup of H. So that's why the quotient group H by H intersection N can be formed. Now what is Hn by N? Hn by N contains these elements of the form Nx such that X belongs to Hn. Now if it belongs to Hn, that means X can be expressed as small h into N, where H belongs to H and small n belong to N. And what is H intersection N by H? It is contain the elements of the form Hy such that this Y must belong to both H and Y, that is belong to their intersection. Now let us define now a mapping from H to Hn by N. I need to show that this mapping F is a homomorphism and it is on 2. So if we define it in this way as Fx is equal to Nx, where X belong to Hn. Okay. So now let us show that it is a homomorphism. So you take this one, let X and Y belong to H. What is f of xy? F of xy is equal to nxy, because we define fx is equal to nx, but you have to replace n by x by xy, so it will become nxy. So now this will implies that fxy is equal to nnxy, because n is a subgroup of G or a subgroup of G, so n will be the same as nn. But since n is also given to be a normal subgroup of G, so this will imply that nx is same as xn. So this will be nx and y, which is equal to fx into f of y. So this clearly implies that f is a homomorphism. Now how to prove that f is on 2? F is on 2 means that every elements of Hn by N must have a pre-image in H. Now what are the elements of Hn by N? The elements of Hn by N will be of the form this one, Nx such that X belong to Hn. So now let us start with this one. So to prove that f is on 2, I need to show that every element of this one has a pre-image in H. So for every Nx belong to Hn by N, there must exist a pre-image in H. So here, let us start with this one. Nx belong to Hn by N will implies that, or this X belong to, for every Nx belong to Hn by N implies that X belong to Hn. So now this implies that X belong to Hn also, Nh. Because Hn is same as Nh if N is a normal subgroup of G. So by the theorem on that one, Nh is same as Hn if N is a normal subgroup. So therefore, if X belong to Hn, it will imply that X belong to Nh. Now if it belongs to Nh, implies that X can be expressed as small n into small h, where N belong to N and H belong to H. And this will implies that if we multiply capital N on both sides, it will be Nx is equal to Nn into H. But this element N is in N only, so it will get absorbed in N. So that is N into N will be same as capital N. So Nx now will become Nh, because this small element N get absorbed in that subgroup N. So now we can see that Nx is equal to Nh. For every Nx, where H here belongs to H. So now you see that for every Nx belong to Hn by N, we can express Nx as Nh where H belong to H. But what is the mapping f defined from h to hn by n? It is defined as fx is equal to nx, where x belong to that nh, which means that x also belong to h. So here, since nx is equal to nh, so it means that for every nx, nx belong to hn by n, their x is h belong to h, such that nx is equal to nh, which is same as f of h. So which means that this nx has a pre-image h in that one h. So therefore f is on 2. So now the mapping f defined from h to nh or hn by n is an onto homomorphism. That means it satisfies the condition of the fundamental theorem of group homomorphism. Therefore, by that fundamental theorem of group homomorphism, h by kernel of f must be isomorphic to hn by n. So now what we are left to prove here is that this kernel of f must be equal to that intersection h intersection n. So for this one, we know that kernel of f will contain this element x belong to h, such that f of x is equal to n, because f is a mapping from h to hn by n, where n is the identity in hn by n. So for this one, let us take x belong to kernel of f and show that this will belong to their intersection. So it means that f of x is equal to n. But what is f of x? It is nx by the definition of f. Nx is equal to n, which means that x belong to n. Now here see, x belong to kernel of f, where x is in g, x is in h. Now x is in h, and finally we are able to show that x also belong to n. So which means that x belong to their intersection. So that means every element of kernel of f will also be in their intersection, h intersection n. So it means that kernel of f is a subset of h intersection n. Now conversely, let us take y belong to h intersection n. And this will imply that y belong to h and y belongs to n. Now, y belong to n will imply that ny will be same as n. Now ny is equal to n will imply that by definition, what is f defined from h to hn by n? As y also belong to h, it implies that f of y is equal to n, because y not only belongs to n, it also belongs to h. And by the definition of a mapping defined from h to hn by n, we define it as f of x is equal to nx, where x is in h. So therefore here also y belong to h and ny is equal to n will implies by the definition that f of x is equal to nx. So here it will be f of y is equal to n. So if fy is equal to n, that means this y must belong to kernel of f. That means any y belong to their intersection also implies that y belong to kernel of f, which means that h intersection n is contained in kernel of f. And now you can see from here, from this equation and this equation, this 2a is a subset of b and b is a subset of a is possible only if these two sets are equal. So that means h intersection n is equal to kernel of f. Then after that you can substitute it here. So finally we got this theorem: h by h intersection n is isomorphic to hn by n. Now I hope it is clear with this explanation. You just go through again, so that in next lecture I'll explain to you this one, the inner automorphism. I'll define the definition of that inner automorphism and also the theorems related to that, which is also another important theorem.